Let's go ahead and talk about scatter plots once more. And let's try to take the discussion back over to statistics because we want to talk about correlation, what it is, the formula, and how we got the formula and how it's used. Okay, so recall what a scatter plot is. It's a type of graph that you can use to describe bivariate data. Before we take up the discussion of linear regression and correlation, okay, we're going to graph a scatter plot. So take a look at this next example here. I got these examples out of the OpenStax free textbook for Intro to Stats. Here's our example. Amelia plays. So what we want you to do is be able to graph a scatter plot on your calculator real quickly, and then just be able to take a look at it and just determine from looking at it, does it appear that there is a linear relationship between the two variables x and y. So let's get you going on that. Amelia plays basketball for her high school. She wants to improve to be able to play at the college level. She notices that the number of points she scores in a game goes up in response to the number of hours she practices her jump shot each week. She records the following data, and they want us to construct a scatter plot and take a look at the plot and see if what she's saying appears to be true. And of course, you can just take a look at the you can just inspect the x and y table here. Notice the x values here are increasing, and that's the number of hours practicing. If she increases her number of hours, does it look like these numbers start to increase? And it looks like generally they might. They do. It looks like generally they do. So I think we're going to answer the question is yes. But let's go ahead for giggles and grins and take a look at the graph on the calculator and how easy it is to get. Okay, so let's go ahead. The instructions to the graphing calculator part are right here. So we want to go ahead and do step one, enter our data into list one and list two. So remember to open the calculator's list environment. We press stat enter. And if you have data in here that you want to clear out, one way to do that is to use your cursor to highlight L1 and press. Alternatively, you can just press the stat button and call on the clear list command. Okay, so let's go ahead and enter that data in. Let's see here, I've got 5, 7, and 12. Okay, so that looks right. Okay, so double checked I've got my data entered in correctly, my bivariate data, my x and y data in my list one and list two. So now I'm proceeding over here to step two. We want to turn our stat plot on. So we want to turn stat plot one on. So it says press second stat plot enter. So right up here above the y is the stat plot command. So we're going to press second y equals and then hit enter. And we want to make sure that our stat plot one is on. If it's not on, then we move our cursor to highlighting to where it highlights the word on and press enter. Okay, so the next thing is we want to do step three. We want to identify the type of graph that we want the calculator to display. Okay, so the way to do that is to arrow down and then arrow over to, whoops, I passed it actually. The graph of the scatter plot is the first icon, and then I'm going to hit enter. And now I've got to tell the calculator where my bivariate data is. Remember, it's in list one and list two. So I need to make X list L1 And if your L1 isn't showing, then remember to put it up there. You just press second 1. And now I'm going to change my Y list to L2. So I'm going to press second 2. And now I'm ready to, let's see here. I guess I'm following these directions. Just press graph zoom 9. Let's see here. For the mark, it doesn't really matter how you want it to mark your points. Make sure there are no other equations. So this is an important step here in step 6 right here. Make sure there are no other equations that could be plotted. Okay, so to do that, you're going to press Y equals button. And I wasn't expecting to get that at all. So I'm going to quit to the home screen to check to see, to go ahead and do the step 6. Now I'm going to press Y equals and just make sure that all of these entries here are cleared out. Okay, so then I'm ready to, well, it doesn't tell you down here to press the graph button, but I'm ready to press the graph button. I don't see anything, but that's okay. I'm going to press zoom 9, right? You're going to press the zoom key and then 9 for zoom stat, and the calculator will fit the window to the data. So I'm pressing zoom 9, and you can see the graph of the scatter plot, and it looks like it's a pretty linear. There's a strong correlation between X and Y, and that correlation looks like it forms a linear pattern. So these are the types of things that we're looking for. And let's take a look at an example from the textbook, which is an application of using the scatter plot and correlation and regression. And this might help motivate the subject here. So this is on page 160. This is from the Roxy Peck book, first edition. And take a look at this this application. I think it's very, very interesting that this was done. Forensic scientists must often estimate the age of an unidentified crime victim. Prior to 2010, so we're trying to find the age of somebody who was a victim of a crime, and like a murder, or it could be something like that. Prior to 2010, this was usually done by analyzing teeth and bones, and the resulting estimates were not very reliable. A groundbreaking study described in the paper, Estimating Human Age from T-cell DNA rearrangements, examined the relationship between age and a measure based on a blood test. Okay, so they established a relationship, they examined the relationship, and look what they found. They found down here a linear trend. So age and the blood test measure were recorded in this study for 195 people, ranging in age from a few weeks to 80 years. And so if you can imagine what your data set looks like, right? It's a list of bivariate data, X and Y data, and your X value is, of course, your blood, right down here, your blood test measure. Okay, and it looks like for the study participants, that was ranging between -17 and roughly -3 here. So each one of these dots represents a person's, right, blood test measure and their age. So you've got a list of blood test measure numbers here. And of course you have their corresponding age there. And each one of these points or solutions is plotted in the scatter plot. And when you take a look at that, Well, shoot, it looks like there's a linear pattern. And that's very useful because it looks like this test ended up replacing um, the, the, um, the tests that were done analyzing teeth and bones. So where is it? Right down here. Based on the scatter plot, it does look like there is a relationship between the blood test measure and age. Smaller values of the blood test measure, which are over here, tend to be paired with larger values of age, right? If you look at all of these dots up here, they have a lower blood test measure than the dots, say down here. Because the pattern in the scatter plot is linear, the line shown in the plot was proposed as a way to summarize or measure the relationship between age and the blood test measure. This line was then used to estimate the age of a crime victim from a blood sample. So there you go, folks. It's statistics in practice, right? For any of those CSI episodes that we saw before 2010, you know, those guys were, Grissom and those guys and gals were analyzing teeth and bones. And now we have a blood test that's more reliable at determining the age of the crime victim. So it's an interesting application. And so this is one, what we want to do here is we want to be able to randomly gather data, bivariate data, and graph them and inspect to see, is there a linear relationship? And if so, is it a strong enough relationship that it's significant and useful? And if that's the case, what is the best fitting line or the regression line that we could put into the scatter plot? And then afterwards, we could use the equation of that line to make predictions about the Y variable, or about the age, in this case, in the age in years, right? So here, in this application, the regression line equation was used to measure age from crime victims. So if, for example, they had they drew blood from the victim of a murder, and then they used the blood test measure. So that would be a number that comes out of another, the measurement. And once that blood test measure is located, you then put that value of X into the equation and find the corresponding age predicted by what's called the regression line, or the least squares line. So that is something we're going to be doing in chapter 4. So moving right along, going back to scatter plots and visually inspecting them. The scatter plots will show the direction of a relationship between the variables. A clear direction happens when either one of these two cases happens: high values of one variable occurring with high values of the other variable, or low values of one variable occurring with low values of the other variable. Alternatively, a clear direction happens when high values of one variable occurring with low values of the other variable. You can determine the strength of the relationship, and in this case, the strength of the linear relationship found in the scatter plot, and seeing how close the points are to a line, a power function, an exponential function, or some other type of function. But for a linear relationship, there is an exception. Considering a scatter plot where all points fall on a horizontal line, providing a perfect fit, then the horizontal line would in fact show no relationship. Whenever you visually inspect or look at a scatter plot, You want to notice the overall pattern, and any deviations from the pattern. Okay, so if you take a look at this sequence of scatter plots, it illustrates that. In the first graph here, A, we can see that it looks like these points, they don't fall perfectly in a straight line, but there is a linear pattern, and that linear pattern appears strong because these points, if you could draw a line in here or put a piece of spaghetti in here somewhere, those points wouldn't deviate very far away from that line. So the relationship is strong, and the direction. So the strength is strong, the strength of the relationship, and the direction would be positive. And one reason that's the case is because in this case, high values of X occur with high values of Y. And right over here in figure B, right, you can take a look here. Yeah, we've got an upwards linear pattern, or you could put a line in there with positive slope. So it looks like there is a positive linear pattern. That's, it looks like it's pretty strong. Maybe not as strong as this one here, and that's because there's this deviation, right? There's one point in the data that deviates from the rest of the points in the pattern. And down here, you've got another figure. It looks like these points are trending downwards, and it looks almost like you could put a line in there, and that those points wouldn't deviate much from the line, so therefore the strength of the relationship looks strong. And if you could put a line in there, that line would have negative slope. And of course, so that means that the pattern here would be negative. And what's happening is high values of X will occur with low values of Y. So there's a distinction that can be made between negative and positive. And I want to talk about that next, but first let's look at this graph over here. You can tell that these points are somewhat scattered about in a linear trend, but there's a lot of deviations from, if you could put a line in there that best fits, there would be a lot of deviations. And so the pattern, the strength of the relationship between X and Y shown in the graph is weak. And because we can put a line in there with negative slope, we've got a negative linear pattern. Okay, so what I wanted to add on to this was that this, okay, so here it is. If Y increases when X increases, so if you increase the value of X and you see that the Y values are increasing, then you have a positive correlation, or a positive relationship between the two variables X and Y. And when we say that it has a positive correlation, we're talking about the direction of the relationship between the two variables. On the other hand, if when X increases, let's put a when in there, if when X increases, the Y values tend to decrease, then you've got two variables X and Y that are negatively correlated. And continuing on with our study of the graphs, take a look at these two graphs right here. We've got another scatter plot graph right here. And it looks like the pattern here isn't linear, but rather it looks like it could be exponential growth. And this is something you'd probably see in a time series of COVID cases. And here's another graph of a scatter plot, and it doesn't appear that there's any type of relationship or any type of pattern between X and Y at all. So a lot of times you've got a research project in which you're interested in studying two variables and whether or not they're related. And the simplest way to do this is to check and see for a linear relationship. And then if you've determined there is a significant linear relationship, as there was in this crime scene example here in the blood test, then it's time to find out, well, what's this best fitting line, and can we use it to make predictions and make a new scientific test in this case, or a new application. So in this chapter, we're going to be mainly interested in scatter plots that show a linear pattern. Linear patterns are quite common. The linear relationship is strong if the points are close to a straight line, except in the case of a horizontal line where there is no relationship between X and Y. If we think that the points show a linear relationship, we would like to draw a line on the scatter plot. This line can be calculated through a process called linear regression. However, we only calculate a regression line if one of the variables helps to explain or predict the other variable, or in other words, if we've determined that the linear relationship is significant enough to justify having the best fitting line, right? If all the points are close to the line, then we're going to use the best fitting line, or the regression line equation, to predict a value of Y for a given X value. Okay, let's go ahead and talk about Pearson's sample correlation coefficient, or simply the correlation number. Pearson's sample correlation coefficient is going to be represented by lowercase r. That's a number. It's also a percentage as a decimal, which measures the strength, the percentage strength, and direction, whether it's positive or negative, of a linear relationship between two numerical variables. Pearson's sample correlation coefficient is a formula that we're going to explain shortly here. But first, let's go ahead and investigate some of the general properties of R, the correlation coefficient. So here I am on, it's page 163 of the first edition Roxy Peck's book. And let's take a look at the table of graphs that she's got here. Consider the table of 8 scatter plots that I'm about to show you here, and their associated values of the correlation coefficient. Keeping in mind that R measures the strength and direction of a linear relationship, look at the table, or look at the graphs, the 8 graphs, and try to answer the following questions. When is the value of R positive? When is it negative? For positive linear relationships, as the value of R increases, is the linear relationship getting stronger or weaker? And what is the largest possible value of R and why? What is the smallest possible value of R and why? And last question here, if R is negative 0.7 for one data set and R is equal to 0.7, positive 0.7 for another data set, which data set has the stronger linear relationship? So let's take a look and see if we can answer those questions together. So here's there's eight total scatter plots here in the table. And here's the first two. Let's see here, there was 8, right? You said, yeah. So the first two, when you take a look at this scatter plot, well, gosh, it looks like these points are falling perfectly along a line. And also, we're told that R is equal to 1. All right, and remember that R, I told you that R is a number that represents a percentage strength of the linear relationship. So here, and it's the percentage strength as a decimal. So here you've got 100% correlation or 100% association, linear association between X and Y here, because all of these points fall perfectly along the line. And so therefore the R value will be 1 or equivalently 100%. And compare that with scatter plot number 2 here. You can see that these points do fall in a generally along a line with upwards trend, although there's a lot of deviations. They don't fall perfectly along a line. If you could put a line in there or a piece of spaghetti, those points in there may not deviate that much from a line with positive slope. And so the value of R is 97%. So these two variables here, X and Y, are about 97% correlated. So that indicates a strong correlation, but not a perfect correlation or 100% correlation as you see here. And when you talk about the direction of both of these correlations here, they're both going to be positive. And one way of looking at that is because the line that you put in there has positive slope. And one thing that we might notice here is that between the sequence of two graphs here, the value of R tends to decrease. So it looks like when the correlation coefficient R is getting smaller, it looks like there is less of a correlation. And going back to scatter plot 1 and this question right here, what is the largest value of R and Y? Well, the largest value of R is going to be 100% because remember the correlation number or Pearson's correlation represents the percentage strength of the linear relationship between X and Y as shown in the scatter plot. And that's given by a formula we're going to look at shortly. So the largest value of R will be 1 or equivalently 100% because you can't have two variables that are correlated 110% or 120% and so on. And let's go ahead and take a look at some of these other scatter plots in the value of R. So we'll just examine the next two here. We've got a scatter plot here, it's 3, and it looks like the points are somewhat generally falling along a straight line with positive slope. And so the value of R is positive. But there's a lot, if you could put a line in there, my gosh, where would the best fitting line be? And also, it doesn't matter where you put that line in there, you're going to see a lot of deviations, a lot of points deviating away from that line. And so the strength of the correlation or the strength of the linear relationship amongst X and Y here isn't as strong as it was in the previous two scatter plots. And you can see that the value of R is also decreasing. So when the value of R tends to decrease, right, what happens? Your scatter plot has the points on the scatter plot deviating a lot more away from a best fitting line. And that can also be said or seen here with the next scatter plot 4 and 5. You see what happens. The sequence of R values is shrinking. And of course, the scatter plots tend to look not necessarily linear. Once you get down pretty close to 0 here at 0.35, and at 0, it looks like there's no correlation. So when there's no correlation, the value of R will be 0. So, or in other words, there's a 0% strength of the linear relationship between X and Y. In other words, it's non-existent. And when you take a look at scatter plot 6, the value of R is negative. And when you take a look at the points of the scatter plot, it looks like they might be, there's a pocket of points that might be trending downwards, or you could almost put a line there with, I don't know if that's the best fitting line right there or not. But you can see there's kind of a downward slope to that line. And very faintly, you can tell that, or it looks like that as X increases, the Y values decrease. And so you're going to have a negative relationship, a negative correlation, or a negative value of R, which is seen here. But also this, remember, this is going to be a percentage. And what we're saying here when we say R is equal to negative 0.26 is that the percentage strength of the linear relationship is about 26%. So very weak. And of course, you can see that in the graph. And the reason why the value of R is negative is to show the direction of the correlation, the weak correlation. It's a negative weak correlation, which means if you did put a best fitting line in there, it would have a slope that is negative, right? Or in other words, somewhat generally, it seems like as X increases, the Y values decrease, but that's not as strong of a value of R as, say, the one shown here in scatter plot 7 and scatter plot 8. So both of these two scatter plots also show a negative correlation, and the correlation is strong. And if you look at scatter plot 8, you can all of these points fall along a straight line, and that line would have a negative slope, and so the value of R is negative. And remember, the strength here would be, in this case, 1 is equal to 100%. So the strength of the correlation, the linear relationship between X and Y, is perfect, or 100%. Whereas over here, and it's also negative, right? Whereas over here, the strength of the relationship, the linear relationship or the correlation, is about 75%. And you can see that there's some deviations. If you could put a line in there, that line would have negative slope. And so that's another reason why the correlation number R, or Pearson's correlation coefficient, is negative. Okay? So that's a quick introduction of Pearson's correlation coefficient, or simply the correlation coefficient. And remember, we're going to use R to represent that number. That number is given by a formula which I'm about to show you. But before I show you, let's go ahead and take a look at some of the properties of the correlation coefficient that you might have seen illustrated in the 8 pictures that we looked at and discussed. And here they are. So if you take a look at property number 1 here, the sign of R, whether it's positive or negative, matches the direction of the linear relationship. R is positive when the linear relationship is positive, and hence the best fitting line would have a slope that was positive. And the direction of the linear relationship is negative when the linear relationship is negative. Okay, so when the correlation is negative, the value of R is negative. When the correlation is positive, the value of R is positive. And property 2 here, the value of R is always greater than or equal to -1 and less than or equal to -1. So another way of saying that is R is in between -1 and 1. I told you can think about R like it's a percentage strength of the measure of the linear relationship between X and Y. And the values of R that are output from the formula I haven't shown you yet will be decimal numbers between and including -1 and 1. And you can multiply each one of those decimal numbers by 100 to get the percentage strength that R is equal to. So another way of stating property 2 is to say that R is between -100% and 100%, but we're just going to use the, we're not going to use the percentage, we're going to use the decimal equivalent here, and that's what's historically done. So what else is she saying about this? A value near the upper limit, or near the upper limit, this number 1, indicates a strong positive relationship. So here's a graph right here with your R-axis. And that's what she's saying here. If the value of R is close to 1, well, then you've got a strong positive, right, relationship. And when you say strong positive, you're indicating what the direction and strength or magnitude of the relationship is. Whereas right here, whereas a value close to the lower limit, -1, suggests a strong negative relationship. And what else is she saying? Figure 4.5, let's see here, that's this figure. Shows a useful way or a good scale here to help remember how to classify the relationship based off of the value of R. If the value of R is 0, there is no correlation. And furthermore, if the value of R is between 50% and negative 50%, or in other words, 0.5 and negative 0.5, then it's a weak relationship. So if I've got a value of R between 0 and 0.5, I'm going to say it's a weak positive relationship, and you're going to see that in the graph. If I have a value of R between negative 0.5 and 0, then I've got a negative weak correlation. And similar statements can be made for other sections of the graph right here. If the correlation number R is between 0.5 and 0.8, we say that the correlation is positive and moderate positive. But if it's between 0.8 and 1, then we're saying that the correlation is strong positive. And then over on this other end, you could say make the same two statements. If R is between negative 0.8 or negative 80% and negative 50%, it's a moderate negative correlation. And if R is between -1 and negative 0.8, you've got a negative strong correlation. And of course, if you have study results that show a strong correlation, that might be useful. But of course, you never want to manipulate study results. So let's take a look at the rest of the properties that are listed here. When the value of R equals 1, so R equals 1 only when all the points in the scatter plot fall on a straight line that slopes upward. So we're talking about a picture like this. And similarly, when R is equal to -1, only when, let's see here, R equals -1 only when all the points fall on a downwards sloping line. So yeah, when all of your points in your scatter plot, and if this is sample data, this is probably never going to happen, but when they all line up, and the line you could put in there would have a downward slope, then the value of R is going to be -1. And we say there's a perfect negative correlation. Finally, properties 4 and 5 here. 4, R is the correlation coefficient. It's a measure of the extent to which X and Y are linearly related. So here's where I'm saying you can think about it as a percentage strength of the linear relationship. How strong is the linear relationship as a percentage? So it measures the extent to which the points in the scatter plot fall close to the straight line. So it measures the deviations and sees if they're small or large. even if the value of R is close to 0, there could still be a strong nonlinear relationship. So what they're saying is you could look at a scatter plot that is clearly not having a set of points that are falling in a straight line, but you can tell that there's some other type of strong pattern. In the case of this scatter plot right here, okay, it looks like there's an exponential, right? There's not a perfect correlation here. There's not a linear correlation. So you're probably going to get a value of R for this data set that is close to 0. But at the same time, even though the linear correlation is relatively non-existent, or is non-existent for this data set, there is a strong nonlinear relationship that can be modeled by an exponential curve or an exponential function. And then finally, property 5 here, the value of R does not depend on the unit of measurement for either variable, because when you look at the formula, the numbers that are going into the formula will not have any units on them. And so the input is a pure number, the input is pure numbers with no units, and the output of the R formula is pure numbers with no units. Okay, so what I'd like to do now is give you a few examples, and then afterwards we'll take a look at the formula for R, which involves using z-scores, and then when there's time left, I'll do a couple more examples showing you how to use the calculator to get important facts that you might need and numbers to answer questions that come up, okay? So what I'd like to do is I'm going to navigate over to the course Canvas page, and I'm looking for, let's see here, my web page down here, down to the lab. Yeah, down here at the lab section of my web page, I'm going to take some problems here from lab 6 right now, which is on correlation. And so it looks like this. And I'm not going to do the problems one after the other, but I do want to, let's just go ahead and hone in on, or I want to take a look at these problems 5 through 11 and explain how you might answer these, how you think about answering these questions, okay? So recall that correlation is a number that measures the percentage strength and direction of a linear relationship between two variables. And the correlation can be either positive, negative, or 0, or a correlation close to 0. And that's what they're asking us to do here. They're asking us to explain whether or not we think that two variables that are given have a positive, negative, or correlation close to 0. And so here's how I think about these problems, okay? I'm going to ask myself, what happens to the y value when x increases? If the y value is increasing when x increases, then I've got a positive correlation. And if it decreases as x increases, then I've got a negative correlation. So let me go ahead and summarize those facts for you here. Okay, so I'm going to give you a guideline for answering this question. I already said it, but here it is again. Whenever I try to answer a question of this flavor, I have to ask myself, what happens to the y variable when x is increasing? Okay, so then if the answer to this question is that y increases, we've got a positive correlation. If y decreases, we've got a negative correlation. And then if you don't think if it neither increases or decreases, then we think the correlation is close to 0. So that's what I'm going to write down now. So there you have it, folks. We're trying to answer questions 5 through 10 on this lab 4 here. And one of the correct answers is either positive correlation, negative correlation, or correlation close to 0. So in each case, I'm going to ask myself this question and then figure out which one of these 3 cases I have. So now if I take a look at question 5 over here, okay, X is the daily hours of sunlight in minutes, and Y is equal to the daily growth of plants in millimeters. So I'm going to ask myself, what happens if I allow X to increase? So if I increase the amount of daily hours of sunlight, is Y going to increase or is it going to decrease? Well, if I increase the hours of sunlight, will it have a tendency to make the growth of the plant decrease? No, it'll probably increase. And so therefore, we're going to say that the correlation is positive for number 5. And taking a look at number 6 here, X is the number of wolves per square mile, and Y is the number of elks per square mile. And so we're going to ask ourselves, what happens to the number of elks when the number of wolves per mile increase? So if you increase the number of wolves, then the population of elks will probably start to decrease. Okay, so the Y value will be decreasing when X increases. So in all cases, I'm going to ask myself what happens to Y when X increases. Okay, so here the elk population or the Y values would probably tend to decrease when X increases. And so the correct answer for 6 is we expect a negative correlation. And then in problem 7 here, let's see, X is the height of a student in a high school, and Y is the grade point average for that student. And so now I'm asking myself, okay, if a sequence of students' heights start to increase, does that mean that their grade point average will go up or will go down? And clearly, folks, those two variables are not correlated whatsoever. It doesn't seem there's any type of relationship to that of X and Y. So there, question number 7, we would say that we believe the correlation is close to 0. And then in problem number 8 is interest rate and number of loan applications. So what happens when the interest rate goes up? Do people want to take out a loan, or are they more likely to take out a loan when the interest rate goes down? So now I'm asking myself this question over here. I'm allowing X to increase. As the interest rate starts to creep up and increases, the number of loan applications will actually decrease because less people will be ready to apply for that loan for the home, or the businesses will be less likely to apply for that loan because it comes with so much interest. So the correlation will be negative for problem number 8. Okay, so that's how you answer a question of that flavor. Let's take a look at questions 12, 13, and 14 real briefly here. Let me zoom out so we can see the question. Okay, so the question is this. For each one of the lines below, I think that should say linear equations, identify values for the slope and the y-intercept. Well, that's fairly easy, folks, right? We know that, at least in this class anyways, that linear equations will have the form a plus bx, a plus b times x. And we also know that, and it looks like each one of these equations is in that form. And we know that a is going to be the y-intercept. And we know that b is going to be the slope. So this problem just simplifies down to trying to identify these two different values of a and b. Okay, so that's how you answer those questions.